we'll be uploading the tutorial sheets. I hope everyone received a notification for the meeting, right?
Yes, ma'am.
Yes, ma'am.
Okay. Yeah, so we'll be uploading the tutorial sheets between Friday to Sunday. Before the week, we start with our we start with the classes for that tutorial, so that you can have a look at the questions and try to attempt all the questions before coming to the tutorial, so that we can first discuss the doubts that you have in some particular questions, and then we can move on to the others. So, any one of you has any doubts and they have had a look at the questions and have any doubts, we can first discuss that, and then I'll discuss the other questions. Okay, so I assume no one has any doubts. So I'll start with question 1. If you have any doubts, you can interrupt in between and ask. Okay. My screen is visible.
Yes.
Yes, ma'am.
Okay.
Yes, ma'am.
First question. Calculate the loss in watts per kg of a current carrying conductor in terms of resistivity rho, the current density sigma, and the specific gravity S. So in this, the units that they have given are not in the SI unit system, so we have to make a few conversions. So we'll keep that in mind. So we take the resistivity and convert it into micro ohm millimeter. So from micro ohm centimeter, that becomes 10 times rho. And the loss is I square R, substituting R as rho L by A and I as current density times area, that is sigma A. We get this. Over here, we have taken L and A in meters. So simplifying this, we get sigma square 10 rho AL. So this micro ohm gets cancelled out with the conversion of uh, sigma, which is in ampere per millimeter square. So finally, this is the loss, and loss per kg will be the loss divided by the weight of the conductor, that is specific density times volume, area into length, and we get the final answer as 10 sigma square rho by S. Question 2. A source of EMF E volts and internal resistance R supplies current to a heating coil. Calculate the resistance R of the coil so that heating takes place most rapidly. And the second part is 3 by 4th of the total energy developed by the generator is absorbed by water. So the heat supplied is equal to the loss in the resistance R, which is given by I square R, where I is taken as E divided by the total resistance, that is internal resistance plus the external resistance R. So this is I square R. Now for maximum heat supplied, we have to differentiate this heat supplied with respect to R, and we differentiate it and equate it to 0. Solving this equation, we get that the capital R should be equal to the internal resistance small r of the circuit to get maximum heat. And this is also the maximum heat transfer theorem that I think will be covered in class. So the second part was that we wanted 3 by 4th of the total energy developed by the generator is absorbed by water. So total energy developed by the generator is voltage into current. So voltage is E, current is E by capital R plus small r. So this is the total energy developed. Now we want heat supplied, which we have calculated in the previous part as this, equal to 3 by 4th of the total energy developed. So we equate these two and we solve for capital R, which by solving this we get that capital R should be equal to 3 times the internal resistance small r. Third question. A coil of inductance L equal to 0.25 Henry and negligible resistance is connected to a source of supply represented by V equal to 4T volts. If the voltage is applied at T equal to 0 seconds and switched off at T equal to 5 seconds, find the maximum value, the RMS value of the current, and the energy stored during this period. Okay, so the inductance is given as 0.25 Henry and the voltage as a function of time is 4T volts. So the voltage is applied from T equal to 0 to 5 seconds. Now we know this equation for an inductor, L di by dt is equal to V. Now we substitute V and L and take dt to the other side for integration. So we integrate from time 0 to t and we have taken the initial current as 0 and the current at any time t will be obtained after this integration, which is 8t square. Now the maximum value of this current for the time that is 0 to 5 seconds will occur at t equal to 5 seconds. So this is a parabola. So after t equal to 0 it is increasing. So at t equal to 5 seconds maximum value will be obtained, that is 200 amperes. The RMS value is obtained by the integration of the square of the current with respect to time from 0 to 5 seconds and divided by the total time, that is 5, the root of it. So we can solve this by simple integration and substitution of limits, and we get that the RMS value of current is 89.443 amperes. The last part was we wanted to know the energy stored at t equal to 5 seconds. So energy stored in an inductor is half into Li square. We substitute the value of L and we take the value of I as the value of current at t equal to 5 seconds. So at t equal to 5 seconds, current is 8 into 25. We substitute it over here and we get the total energy stored at t equal to 5 seconds. Question 4. Two coils are connected in parallel and a voltage of 200 volts is applied to the terminals. The total current taken is 25 amperes and the power dissipated in one of the coils is 1500 watts. What is the resistance of each coil? So the two coils are in parallel and they are connected across a 200 volt source. Let the total current that is coming out of the source be I, and this I is given as 25 ampere in the question. Also, the power through R1 is given as 1500 watts. So power is V square by R. V is 200 volts. So 200 square by R1 is equal to 1500, which gives R1 is 26.67 ohms. Now to calculate R2, we can use the fact that the total current is 25 amperes, which is equal to current through R1 plus current through R2. So we can substitute R1 and get R2 as 11.48 ohms. Question 5. A resistance R is connected in series with a parallel circuit comprising of two resistances of 12 and 8 ohms respectively. The total power dissipated in the circuit is 70 watts when the applied voltage is 20 volts. Calculate R. So we have 8 and 12 ohms which are in parallel and these are connected in series with a resistance R, and this combination is connected across a 20 volt source. So first let's calculate the effective R of this circuit across 20 volts. So that will be R plus the parallel combination of 8 and 12 ohms. So this is equal to R plus 4.8 ohms, and the total power dissipated in the circuit is 70 watts. So this is equal to V square, that is 20 square by R effective, which gives R effective is 5.714. So equating this 5.714 to R plus 4.8 ohms, we get that R is equal to 0.914 ohms. Question 6. A wire is bent into a plane square of 12 inches side and a current of 25 ampere is circulated round it. What is the magnetic field density at the center of the square? So this is the arrangement. So we can calculate the magnetic field at the center of the square. So for one particular conductor, we use this formula. You might have studied this in JEE itself. So you use this formula for one conductor where θ1 and θ2 is the angle that the ends of the conductor make with the point where we want to measure the magnetic field. So over here, substituting the value of θ1 and θ2, and A is the side of the square. Over here, we will add the magnetic fields of all the four conductors, because by right hand thumb rule we see that the direction of magnetic field due to all the four conductors is the same. We get that the net magnetic field at the center is 2 root 2 mu naught I by pi A. Directly substituting the values of A, I and mu naught, we get that the magnetic field is this 0.927 into 10 raised to minus 3. So this is just a recap of the magnetic field formulas that you have already studied. Question 7. 2 voltmeters A and B having resistance of 5000 ohm and 15,000 ohm respectively are joined in series across 240 volts. What is the reading of each voltmeter? Okay, so these are the 2 voltmeters. Their resistances are given and they are connected across a 240 volt source. So we can calculate the voltage across V1 by simply calculating the current across the circuit into the resistance of this voltmeter. So current is 240 by the total resistance of the circuit, addition of these two into 5000. So that gives 60 volt. Similarly for V2, we can calculate the voltage by 240 by total resistance into 15,000. So that is 180 volt. Question 8. An air condenser consisting of two parallel square plates of side 50 centimeter is charged to a potential difference of 250 volts. What is the plate when the plates are 1 millimeter apart? Find the work done in separating the plates from 1 millimeter to 3 millimeter and assume perfect insulation. Okay. So when we increase the separation, the charge will remain the same, but there will be a difference in the energy. So the change in energy will be equal to the work done. So let's calculate the initial charge on the capacitor. That is equal to C times V. V is 250 volts, and we can calculate C using this formula where A is the area of the plates and D is the distance between the plates, and this is permittivity is constant. So A is equal to 50 into 50 square centimeter and D is 1 millimeter. So substituting this value over here, we get Q equal to 553.386 nanocoulomb. Similarly, we can calculate the final capacitance by changing the distance between the plates. So the net energy change will be half into Q square by C, and C will change from C final to C initial. So we directly substitute the formula for C, and here df minus di will change from 3 to 1 millimeter. So substitute the values and you'll get the answer in joules converted into this different quantity for energy, and the conversion from joule to erg is this 1e7 ergs. Yeah. So question 9. A resistance of 10 ohm is connected in series with two resistances, each of 15 ohm, arranged in parallel. what resistance must be shunted across this parallel combination so that the total current taken shall be 1.58 ampere with 20 volt applied. Okay, so the arrangement, so for 1.5 ampere and 20 volts, we need a total effective resistance equal to V by I, that is 13.333 ohms. And by adding the resistance X, which we need to calculate in parallel with the 215 ohm resistances, we get a net arrangement in which the 215 ohm and X are in parallel, and this combination is in series with the 10 ohm resistance. So we equate this equal to 13.33, and solving this equation for X, we get that X is equal to 6 ohms. Question 10. A constant voltage E is applied to n groups of rheostats in series where each group has m identical rheostats in parallel. One rheostat burns out in one group. Find the percentage increase in current in each rheostat of the faulty group. Okay, so first of all, let us assume that the resistance of each rheostat is small r. So we have n groups of rheostats in series, and each group has n parallel rheostats. So before the rheostat burns out, first let us calculate the voltage across one of these n groups which are in series. So that will be E by n because all the groups are identical. Then we calculate the current in one rheostat of these the group which has m parallel rheostats. So that will be the voltage across one rheostat divided by its resistance. Now after burning of the rheostat, the total resistance will be now n minus 1 groups uh, have the rheostats which are m in number and they are in parallel. So the m rheostats in parallel have an effective resistance of R by m, and this effective resistance is there n minus 1 times. So R by m into n minus 1, and then one group is there in which there are only m minus 1 rheostats. The mth rheostat has burned out, so it is now effectively an open circuit. So m minus 1 rheostats in parallel will give an effective resistance of R by m minus 1, and this is in series with the other rheostats. So this will be the net total resistance. Now the current will be the voltage upon the effective resistance that we calculated. Now current in each rheostat of the faulty group Y will be um, the current uh, the current divided by m minus 1. So it will be divided in the m minus 1 rheostats, and we can calculate the percentage increase by y minus x by x into 100. This is y and this is x. Okay. Question 11. A cell supplies 48.8 milliampere to a 25 ohm load and 25.9, this is milliamperes, like there's a typing mistake over here, to a 50 kilo ohm load. Determine its EMF and internal resistance. Assume both to be constant. Find the terminal voltage of the cell when connected to a 40 ohm load. So for the first cell, this is the EMF. For the first equation, this is the EMF of the cell and this is the internal resistance. So E minus the drop across the internal resistance is equal to the drop across the external resistance. And the second equation will be E minus the drop across the internal resistance when current is 25.9 milliamperes is equal to the drop across the external resistance. So just solving these two equations, we'll get EMF and the internal resistance. Now when we connect it to the 40 ohm load, the terminal voltage will be E minus I times the internal resistance, and we can calculate the current in the circuit by writing current as E by 40 plus R, that is the total resistance in the circuit. So substituting the values of E and R from the previous part, we get the terminal voltage as 1.275 volts. Question 12. A 20 volt battery with an internal resistance of 5 ohm is connected to a resistor of X ohms. If an additional 6 ohm resistor is connected across the battery, find the value of X so that the external power supplied by the battery remains the same. Question 12. Yeah, so the initial arrangement was that the X ohm resistor is connected across the battery, which has internal resistance of 5 ohm. So the external power will be the current in this the current in the X ohm resistor, square of the current in the X ohm resistor times X. So the current is taken as 20 by 5 plus X. So this is the external power. Now when a 6 ohm resistor is connected in series with this X ohm resistor, similarly we can find the external power by using instead of X using 6 plus X and equating these two external powers as asked in the question. We can solve for X and we get the value of X as 2.83 ohms. Question 13. Two 12-volt batteries with internal resistance 0.2 ohms and 0.25 ohm respectively are joined in parallel and a resistance of 1 ohm is placed across the terminals. Find the current supplied by each battery. So this is the arrangement. There are two 12-volt batteries with their internal resistances and a 1 ohm resistor is connected across this arrangement. So taking the current in this branch as I1 and this branch as I2, we can this branch will have current I1 plus I2 by applying KCL. So after that, we to find I1 and I2, we can directly apply KVL in two loops. So let's first apply KVL in this loop, that is FCDE. That will give 12 minus 0.25 I2 is equal to I1 plus I2. Similarly, applying KVL in A, B, D, E group, we get this equation. Solving these two equations, 1 and 2. Is there a message? Yes, we'll upload the solution PDF. But it will be uploaded by the end of the week when all the tutorials are done. Yeah, so applying KVL in the loop ABD, we get this equation. Solving these two equations, we get the value of I1 as 6 amperes and I2 as 4.8 amperes. Question 14. Two heaters A and B are in parallel across. Yes.
In this question, like if we just apply nodal analysis and if we take one point as zero, like yeah, this question,
Yeah. This right?
yeah, like if
Yeah.
we take point, suppose we take point A, F, and E as zero potential,
Hmm.
yeah, and then if we just apply nodal, then it's easier to calculate. Then 12 by 0.25, so
Hmm.
it will be 48 ampere, and the answer is 4.8. Similarly, in the other one also it is 60 amperes.
Yes, you can do that.
Yeah, but
Like for
we get
node,
different answers, right?
so for nodal analysis, what you have to do is first you have to convert, um, when you do it in nodal analysis, you convert the EMF source into a current source, right? So what you are calculating is the value of current in the current source branch. And but this resistance, the 0.25 ohm resistance, will come in parallel with the current source. So this is not the effective current inside this branch. That is the current only for the current source. Are you getting my point?
Can you explain it again?
Okay, so when you do nodal analysis, you first convert the voltage sources into current sources, right?
Yes, ma'am.
Okay, so what you will do is you will convert this voltage source 212 by 0.25 ohm. So whatever current value you are getting, you will put a current source over here. But this resistance value will now be placed in parallel with the current source.
Okay.
So the value of current that you are finding will not be the value of the current that is flowing in this actual branch, because now the resistance is in parallel with the source, and that is a current source. So you'll have to solve it using this method only, because we want to find the value of current in this branch.
Okay, ma'am, I'll try that method then.
Yeah. Okay. Question 14. Two heaters A and B are in parallel across supply voltage V. Heater A produces 500 kilocalorie in 20 minutes and B produces 1000 kilocalories in 10 minutes. The resistance of A is 10 ohm. What is the resistance of B? Also, if the same heaters are connected in series across the voltage V, how much heat will be produced in 5 minutes? So this is the arrangement. A and B are the two heaters. So it is given that A produces 15 kilocalories in 20 minutes and B produces 1000 kilocalories in 10 minutes. So A is given as 10 ohms. So for A, the energy produced is given as I square RT, that is 5000 kilocalories. So first we convert the kilocalories into joules. So the conversion is 1 kilocalorie is 4184 joules. And using in place of I square R, substituting V square by R and taking the time in seconds, so 20 into 60 seconds is equal to 4184 into 500, and by this we can calculate the V. Now for V, now for the heater B, substituting this value of V, so V square by R into time in seconds is equal to the energy in joules, so that is 4184 into 1000. We get the value of RB as 2.5 ohms. Now, when A and B are connected in series across V equal to 132.0335, we get that the heat produced in 5 minutes is I square times RA plus RB, the total resistance, into time in seconds, that is 5 into 60 seconds. So replacing I square by RA plus RB, I square into RA plus RB by V square upon RA plus RB, and substituting the value of V, RA and RB, we get the heat produced in joules. And then since the answer is given in kilocalories, uh, converting joules to kilocalories, we'll get 100 as the answer. Question 15. Find the equation of the voltage to be applied to a 50 microfarad condenser initially uncharged to produce a steady current of 10 milliamperes. If the charging ceases after 10 seconds, calculate condenser voltage, charge and stored energy. So the equation for capacitor is C dV by dt is equal to I, which is equal to dQ by dt. So we know the value of C. We know the value of the steady current, that is 10 milliamperes. So for calculating the voltage, we will use the equation C dV by dt is equal to I. Now I is constant, that is steady. So we will substitute I as 10 milliamperes, and the charging time is given as 10 seconds. So we take dt to the other side and integrate from 0 to 10 seconds, and we calculate and we integrate over here from 0 to V. So the initial value of voltage is 0 because it is given that the capacitor is uncharged initially. So Q equal to CV, Q equal to 0, so V equal to 0. Now integrating, we get that the value is V is equal to 2000 volts. The second part, we begin substituting I as 10 milliamperes and integrating from 0 to Q and 0 to 10 seconds, we get that the value of Q is 0.1 coulombs. The last part was to calculate the stored energy. So the stored energy in a capacitor is half CV square. Substituting the value of C and V, uh, we get the value of stored energy as 100 joules. This is the last question. The voltage shown in figure 1 is applied to a 2.5 microfarad capacitor and a 0.5 Henry inductor. No initial current. Plot the scale graphs of IC and IL. Okay, so this is the voltage versus time graph. First, we will plot the graph for the capacitor. So IC is given as C dVc by dt. So first let's calculate dVc by dt from this graph. So there are two lines. So there will be two values of dV by dt. For the first line, the value is 40 divided by 4 milliseconds. So this dV by dt is 10 raised power 4 for time between 0 to 4 milliseconds. And after 4 milliseconds, the slope of this line will be taken into account. So that is minus 2 into 10 raised power 4 for time between 4 to 5 milliseconds. Now IC is the value of capacitance times dVc by dt. So multiplying these two with the capacitance, we get the value of IC, and it is divided in two intervals. Between 0 to 4 seconds it is 25 milliamperes, and between 4 to 5 seconds it is minus 50 milliamperes. So this is for capacitance. Now for inductance. For inductance, it is, we know that V is equal to L di by dt. So taking dt to the other side and integrating. So we first calculate what is V, and then we integrate this V to know what is I. So the V is the equations of these two straight lines, that is this straight line and this straight line. So we already know the slopes of these two straight lines. Taking the intercept and finding their equations, we find that VL between 0 to 4 milliseconds is given as a function of time like this, and between 4 to 5 milliseconds it is given as a function of time in this way. Integrating these from 0 to t, we get IL, and you can do the integrations for the two time intervals. We get that IL is equal to 10 raised to the power 4 t square minus 4t for 0 to 4 milliseconds, and this equation from 4 to 5 milliseconds. So you can do the calculations. And why does the last Q diagram look like? Okay. So like these are pretty straightforward questions. So it was just for a recap of what you have already done. From next time, if you have any doubts, you can ask me right now. And next time onwards, I think network theorem will start. So we'll have a tute on that.
Ma'am, can you check the answer of 13th once?
Yeah, sure. This one? Is it the same doubt that why are we not using a current source?
No, ma'am, I'm getting the same answer.
What method are you using? Are you using KVL?
Yes, ma'am, but however you think about it, like it's only asking you the current through the battery, right? So you can just take it as a separate, like one separate circuit, and this is one separate circuit, this is another separate, like A to B is one, F to C is one, E to D is one. Like you can't take E to D, but F to C is 1. Like if you take it like A points and F points and E points as 0. Yeah. No, I just wanted a confirmation with the answer. That's it.
So if you take A, F and E as 0, how do you know the value of voltage at B, C and D?
We don't know, ma'am. We'll assume it to be X.
And then you'll solve using nodal analysis, right?
Yeah.
So I think by using this also you should get the same answer.
Okay. Yeah, I got it, ma'am. I was making a mistake. Okay, yeah.
You got it right.
I made a mistake of I took them differently, so I got long equations.
Okay, fine. So nodal analysis has been covered in class.
Yes, ma'am. Today, sir just gave brief idea.
Okay, fine. Okay, any other doubts? Okay, if there are no doubts, we can leave then. Meet you next time. The solutions will be uploaded. By Friday, they will be uploaded.
All right, ma'am. Thank you.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.